In this video, I'm going to cover how the passive house building science can support any project in improving the living conditions for occupants in different climate zones. Before doing that, I'm going to introduce EMU a little bit. This is our team photo this summer in the Rocky Mountains, and the map shows the locations for the passive house boot camp workshops we've had so far in 2022. And we used to be architects. We no longer practice, but that is what our background is. And I am personally a registered Italian architect. So that is, when we think about buildings, we really try to put people first, and we also try to improve the energy efficiency and to lower the impact on the environment. But really, our mission is to bring the most advanced building science to mainstream construction market in making buildings better at being shelters for people. We have working experience in Italy, Germany, Australia, and the US, and that allows us to have access to a body of knowledge that is international, and it may not even be translated in English yet. So when we do our research, this experience allows us to get information from third parties that may not be available in the US, at least just yet. EMU comes from the Australian bird. It's not an acronym, it's just a bird. And we started in passive house at around 2010. We are now 100% passive since at least 5 years in terms of what we do, and we mostly do builder training, and we also do consulting that is meant to support builders through the first few passive house projects. Now, this year we have become the largest training provider for passive house builders in the country, as well as in Australia. This is the photos at the top are the trailer and some that we take the material for the workshop around, as well as a photo from one of the workshops. In this case, it was Maine. We operate in a very niche market where we really we're lucky because we attract builders and projects that specifically want to go above and beyond, meaning that to us it is normal to achieve 0.3 ACH50 at the blower door test instead of 3 ACH50 that is code minimum. So our buildings are built extremely better than code minimum. And in this context, hitting a 1 ACH50 is basically a failure because passive house is 0.6. And as I said, we feel privileged because it feels like we may be like trainers of Olympic athletes. We attract very smart builders that want to go above and beyond and take pride in the quality of their craft. So that is very rewarding to us, and so kind of what I'm going to present on today is framed by operating in this niche market. That is how the market we hope is going to be in the future, where builders have extreme pride of what they're doing and they're delivering great projects supported by the passive house building science. So today we're going to cover how a performance-based building science handrail can help projects improve not just in terms of energy efficiency and environmental impact, but also how to improve the living conditions for people inside buildings based on the most recent and up-to-date building science, something that building code is decades away from adopting. So start with this question: why do we put numbers on money bills? You know, money is very important commodity, and why do we put numbers on? And so, in my opinion, George Washington was a much better president and person for the country than Benjamin Franklin. So, in my opinion, George Washington is a much better bill than a Benjamin Franklin. Now, would you give me one Benjamin Franklin in exchange for one George Washington? You wouldn't do that. So personal opinions can only go so far. Where we need to make informed decisions, the numbers and facts are extremely important in order to allow us to make informed decisions, whichever they are. So throughout this presentation, we're going to go over some value metrics of how building impact people in different ways. And there are some beliefs in the market that are supported by evidence, and there are many other beliefs in the market that are not supported by evidence. In fact, the evidence shows something completely different. Speaking of that, how long do you think an average family stays in a house before they move out again? They move in today. How many years do you think that family is going to stay in the house before they move out again? Think about that for a sec. If you have thought about 5 to 7 years, you are in the average of what most builders think. The data shows actually that a family stays in the house for about 13 years. So that completely changes the framework of how we talk to our clients in advising them. Because if we believe that they're going to stay in a house for a shorter period of time, then we may be led to advising them to invest less in that house because they're going to move out sooner. The reality is that compared to what most professionals believe, a family stays in that house for about 2 or 3 times longer. So it is advisable to have them invest more in that house because they're going to stay there longer. And this is an example of how there are beliefs in the market that are not supported by evidence. In fact, they are very far away from the evidence, and they impact negatively how we advise our clients about what decisions to make for their projects. Now, they can make any decisions, but we as professionals need to have the data right in order to be the professionals and have the information that the clients need in order for them to make informed decisions. So this is a short summary of what I'm going to present on today. I'm going to touch very shortly about the passive house standard, what it is, talking about performance-based approaches to comfort, durability, and energy efficiency. Then look at face value performance of certain products as opposed to how those products actually perform in the field at day one, as well as how this performance ages over time once the building gets older. So this is the definition of the International Passive House Standard. A building can be certified if it has a heating demand of less than 4.75 kilobtu per square foot a year, as well as a cooling demand of less than 4.75 kilobtu per square foot a year, plus some additional allowance for climate-specific dehumidification, primary energy less than 19 kilobtu per square foot a year, an air tightness level of less than 0.6 air changes per hour at 50 Pascal as measured at the final blower door test. Then there's a specific criterion for indoor air quality that requires continuous balanced ventilation through an ERV or HRV system. There's a comfort criterion which impacts the selection of windows and doors that is specific to the climate. We're going to see that today, as well as prevention of mold and condensation by design, which is called the hygiene criterion. Hygiene is absence of mold and condensation. And this is an analytical approach to preventing mold and condensation that is decades further advanced than what building code currently requires. So it is a way that we professionals can advise and inform decisions of our clients and our builders on how to prevent mold and condensation proactively, as opposed to just building the building and hoping nothing bad is going to happen. If you do that, then your building consumes about 80% less for heating and cooling compared to the same building built according to the 2018 Energy Code. It's all performance-based. Passive House is all based on modeling. There's no prescriptive checklists. You need to develop the building with the support of the PHPP, Passive House Planning Package, modeling software, and that is something that we recommend start doing at the early design stages, such as the schematic design. Coming from Europe, in Europe there is no prescriptive code compliance. It's all performance-based. And when I think about the prescriptive approach is when you already know the answer before you even formulate the question. Think about a project in climate zone 4, or your wall are R20, and your ceiling is R49. This takes no consideration of what the project actually looks like. It does not consider at all the design, nature, exposure of that specific design. It does not ask question, here's your answer. Your climate zone 4, R20 for your wall, and R49 in your ceiling, and all the other requirements. And to me, that is a very dumb way to approach performance and building science, because you literally don't ask questions. You just have a set of prepackaged answers that you distribute flat by climate zone, as opposed to a performance-based approach where you actually listen to the question before you formulate an answer. We're going to see what that means later today. Think about an analogy with the medical world. So think about without a thorough medical exam and probably a second opinion, would you ever start an expensive medical treatment, take restricted medical drugs, or undergo serious surgery without an actual medical exam first and possibly asking a second doctor about their opinion? That is what the prescriptive method is. So to draw an analogy with the medical world, the energy modeling is similar to having a thorough medical exam that tells you how things are going. This picture has X-rays because I see the energy model as X-rays of your building. It tells me how different components are performing with regards to different metrics: thermal comfort, avoidance of mold condensation, as well as energy efficiency. And once you have the information from that exam, then you can make informed decisions about how to move forward. If you don't, you're just guessing. So performance-based for Passive House is a lot of numbers, and we're going to see some today. The good thing is that these tables are actually not for Passive House, they are from construction takeoffs. So builders go through a lot of math exercises with construction takeoffs. And so in my opinion, if you have the patience and strength to survive a construction takeoff, then you have enough brain power to also go over Passive House and survive, because it's actually very fun. This map shows about 50 projects that we put together from our database for a study that we're working on for Passive House. And for these projects and many others, we do Passive House science-based optimization, whether or not these projects want to actually hit Passive House level and certify. So it shows we model about 100 projects a year, typically at the schematic design stage for what we call the preliminary Passive House review. And at this stage, the goals are to inform the decision of a project team in terms of what they actually need to meet the performance goals for their specific climate, and to inform the budget allocations. And performance in that statement is not just energy, it is also thermal comfort. We're going to see how that greatly impacts the selection of windows and doors, which is one of the most expensive line items of the entire budget, as well as indoor quality and energy efficiency. In doing that, we typically see these projects reducing the need for heating and cooling by about 60 to 80% compared to even the 2021 energy code. So great opportunity for improvement compared to code minimum compliance. And about 20% of this project we actually recommend certification and support them through construction. 80% of them, really this process at the early stage allows them to really narrow down what they need so they can make informed decisions of how to develop the project and budget further past the schematic design and optimize their performance for their climate as well as the project specific goals. Top left is an example, one of the many projects that we model. Project in Climate Zone 7, 4-bedroom, 3 stories, form factor of 2.5. We ended up speccing triple pane windows, high solar gains for the glass, R60 walls, etc. Another one for Climate Zone 2, it was a much smaller unit, 2 bedrooms, 1 story, form factor 3.8, and we ended up speccing double pane windows, low solar gains, R20 walls, etc. Now this was a client where this Florida one was a client that was excited about being the first project in Florida to use triple pane windows for passive house. And this is a project that is going to be certified. And he was like, oh yeah, we're gonna be the first one to use triple pane windows. I'm like, no you're not, because you don't need that. And if you don't need something, then don't buy it. What is the need about windows and doors? Why do we need triple pane windows? We don't need triple pane windows, we need to feel comfortable. And Passive House provides you the science that allows you to determine what minimum performance for windows and doors you need in order to get comfortable. So in case of Florida, it never gets that cold, so you do not need the extra thermal protection of triple pane windows. Whereas for the projects listed here in Climate Zone 7, which is super cold, we definitely need that thermal protection. So this is an example of how an energy modeling passive house based approach helped them, 2 different projects, make decisions in terms of identifying what they need and allocating budget resources to meet them. This is something that if you don't have this performance-based approach, you're just pulling numbers out of your butt. You don't have a way to do that. Another example for a project in Seattle, Washington, it was a small one, an ADU, 1 bedroom, 900 square feet, most glass facing west. This is what a table looks like from the project. This is a summary of one of the summaries we had as part of the preliminary passive house review, where we look at the reduction of heating and cooling combined compared to the baseline of the 2021 Energy Code. And you see, out of these 50 or 60 individual scenarios, we highlighted 4 of them, where the reduction for heating and cooling is between 61 and 68%. More importantly, we did a thorough analysis on comfort. So in the metrics that we cover in the analysis, we provide recommendations for the window package in order to determine the comfort requirement. Then we looked at how to optimize the glass for the year-round performance. You see, we called out low solar gains, medium solar gains, and high solar gains. And with the premise that most glass is facing west, if you don't have the support of an energy model, you may lead to believe that you want all of your glass facing west being low solar gains, so that you block off a lot of that heat in the summertime. And that at face value, that is what you may think if you don't have an energy model to give you answers. So if you're pulling numbers out of your butt, you may think that, oh, west facing, always low gains glass, which it really depends on the climate. This is Climate Zone 4C, and this building is in a city. This building is not in a vacuum. We're not building on the moon here. So this building had other neighboring buildings around it and trees, which caused shading. So the models showed that even though most of glass was facing west, For the best performance for heating and cooling, going with medium gains was much better than low gains. And this is something that only the energy model can help you navigate. This is a market, the high performance market, where the moment you start that you want to invest more money in a project, you'll find plenty of people that want to help you do just that, spend more money. Whether you get to the actual performance goals that you want to achieve, that is a completely separate matter. This passive house modeling-based approach really provides you the ability to quantify the impact of option A over option B and C. So how much does A change things and how much does option A matter compared to B and C? If you don't have an energy model, you don't have an analytical way to address that. So it's not that we like energy modeling, we don't like to make up stuff. So we just use the science to help clients make informed decisions. This slide shows the range we're working on in this market today. At the bottom, we see building code. Building code is the minimum level of performance you are legally allowed to build that today. In other words, a code minimum building is the worst building that you are legally allowed to build. That is literally the definition of building code. Then on the other end of the spectrum, we have the gold standard, which is passive house, which compared to the 2018 and 2021 code allows a reduction for about 80% for heating and cooling. Now, in between the two, there's a number of foggy, undetermined definitions or names that kind of confuse the market. Oh, my building is better than code. My building is 20% better than code, based out of having done no modeling, so you don't actually know what you're talking about. My building is high performance. We literally know builders that put 1/4 of an inch more insulation than code minimum, and they call the building high performance. And that is high performance. It is higher performance than the code minimum, so they can say that. Is that passive house? No. Is that actual high performance? It depends. Like, it's not. It can be all the things. And literally anyone down the street can claim they have a high performance building if they put 1/8 of an inch more insulation than code minimum. And that is higher performance than code. There's super insulated, there's super tight, zero utility house, passive solar that is basically passive but haven't done the modeling. And all of these we call the floaters, meaning they float in between the code minimum and passive house. And there is some substantial risk there because you don't have structure. Building code, does provide you structure. It provides you a minimum that you cannot fail. Passive house does provide you structure. It's basically a performance-based building code of the future, and it provides you with very strict requirements that on a performance-based approach you can meet. Those are structures. Anything that floats in between passive house and code does not have this structure. So what are we doing again? It's very difficult to define expectations with the client. If you want to do a code minimum or if you want to do passive house, you have very specific goals. If you don't have these specific goals, everything becomes foggy and very unclear, and it becomes very difficult to determine expectations with the client. It's very easy to overpromise and underdeliver. We're going to see an example of just that today. And it's also very easy to overkill and overpay, for example, for the window package. The client down in Florida wanted to get the triple pane, and had we not done the thermal comfort analysis, they may have gotten the triple pane. They may have spent thousands of dollars more on windows that was unnecessary for the climate location. And it can be underkill in terms of indoor air quality and moisture management. Now, if you think about the analogies that we did for the medical field, think about you go to the hospital, and what makes you feel most confident about the competency of the doctor? Your arm is broken, or your arm is basically broken. Which one of these two makes you feel more confident about the competency of that doctor? It's broken, it's basically broken. This is the same situation we see in the building market. It's better than broken. It feels like it's broken, and you know X-rays are bullshit. And what MD degree? Don't you see the scrubs? Like, there's a lot of like fun you can have, but think about what you hear in the market. Like, oh, it's high performance. Oh, we don't need to do the modeling. I know what it is, and that's bullshit. At the end of the day, we're making a promise to our clients, and we need to deliver on that promise. This is all what this is about. Whichever the promise is, we need to deliver on that. Whether it is passive house certification or not, or code minimum, we promise A, we need to deliver A. And this graph shows the data collected from 25 buildings from the UK, where there was an expectation as far as energy consumption, and then some buildings greatly consume more energy than what was anticipated. So we have the promise, hey, your building is going to need this amount of energy, and there was the under-delivery in that building actually consumed a lot more energy than expected. And this is called performance gap. Now, this graph also shows a few passive house buildings where, because of a number of reasons, the gap was the narrowest on record. And this is typical for passive house, where it's a much more detailed approach. It's performance-based. It's very strict in terms of requirements and quality assurance. And so what you actually promise, you do deliver, as opposed to over-promising and under-delivering. Now, to make this a little bit more fun, I created a little story to describe a process to illustrate how things can go well or poorly depending on the approach you take on a project. So I made up the story of two twin brothers. One is Enrico, this is me, and Enrico has an accent, as you can tell. Is a very much of a square, and he's contracted to build a passive house. And his very evil twin brother, Enrique, also has an accent, Googles a lot, and is contracted to build a house identical to Enrico's. And this is how the story goes. And this is to meet the client expectation. So I took the project of my house in Colorado and moved it to Chattanooga, Tennessee. And it's a single family, 1,500 square feet, 2-story, remodel plus addition. And the goal is for Enrico to meet passive house. This is what the south elevation looks like, and this is what the 3D energy model looks like. So I'm on a ridge, there's trees around, some of them are evergreen, some of them are deciduous. And starting from the bottom up, for the floor in Chattanooga, Tennessee, that is climate zone 4A, I need R15, so Enrico picks 4 inches of EPS under slab, and Enrique chooses 3 inches of XPS under slab. For the exterior walls, we need R30, and Enrico picks a wall consisting of drywall, dense spec cellulose in the 2x6 cavity, plywood sheeting taped to the seams as the air barrier, and then 2 inches of exterior continuous polyage insulation under the rain screen. On the other side, Enrique uses drywall as his air barrier, uses the same dense spec cellulose in the 2x6 cavity, and then uses the 2.5-inch zip R sheeting as the continuous insulation. And then over that goes the rain screen. At the roof, we need an R60 So Enrico uses a smart vapor retarder as the air barrier and 15-inch of dense specs fiberglass in an unvented roof assembly. Whereas Enrique uses the drywall as the air barrier and then 8.5-inch of closed cell spray foam, sheeting, membrane, and finish. Windows and doors, keep in mind that this is what the south elevation looks like. So Enrico is not that concerned about the overheating, whereas Enrique is. And so Enrique uses C-grade passive house frames with warm edge spaces. We don't have too much time to go over this today, but just keep this in mind. Enrico uses beefy triple pane, so the overall thickness of the glass unit is 1.8 inches, basically 2 inches of glass assembly. We're going to see what that means. With 90% argon fill, medium solar gains, and an Indian window install. We're going to cover that later, but you see the building section here where the window is installed in the middle of the insulation thickness. Enrique, on the other hand, also uses a C-grade for the window frame, warm edge spaces, then uses skinny triple pane, so just the overall thickness of the glass unit is 1 inch instead of the 1.8 inch for Enrico. And Enrique has Googled and found out that somebody on the internet says that the argon gas goes away after only a couple of years, so it's not worth investing the money. And so Enrique uses air-filled window glass instead of argon. Enrique is also concerned about the overheating in the summertime, and this is climate zone 4A, so it's like in between heating and cooling dominated. So Enrique chooses low solar gains. And if you look at the building, the wall section on the right hand side, Enrique chooses a more traditional Audi window install, with the window installed exterior to the outside of the wall assembly. In terms of heat recovery ventilation, Enrico chooses a ducted ERV with 87% heat recovery and a MERV 13 intake filter, whereas Enrique uses a ductless HRV, 89% heat recovery. We're going to see what it means. They build the building, they get to the final blow door test. Enrico gets 0.6 ACH 50, yay. Enrique also gets 0.6 ACH 50, yay, everything is happy. So at this point, both of them go to the finish line of the project. And at face value, the two buildings perform the same. So this is where we're happy, we have met the client expectations, we have indoor air quality, we have thermal comfort, we have moisture under control, energy efficiency, it feels good, happiness, joys, puppies, kittens, yay, it feels good. It feels good to finish up a project until it doesn't. And day one, things start to go poorly. And the client starts seeing that the energy consumption, Enrique's client starts seeing that the energy consumption is actually much higher than what anticipated. Actually, it's 2/3 higher than the expectation. So let's see what happens. This is the relationship of what we were talking about, where we make a promise and we have to deliver on that promise. And in this case, we actually under-deliver in that the actual consumption of energy is much higher than what anticipated. In addition to that, Enrique's client has condensation, as well as they are very uncomfortable because they feel cold in the house. So let's see what happened. The C word, which in construction means condensation, Enrico used vinyl flashing, which has a temperature factor of 0.79, whereas Enrique used a very common stainless steel metal sill pan under the window, highlighted in red in the slide, which is very common, but it's also very bad because it basically allows the heat to escape and the cold to get in, causing a cold spot. And Enrique was good enough to Google which metal is less bad, and stainless steel is the least bad metal out there. It's less bad than regular steel, it's less bad than aluminum, it's less bad than copper. These are all metals that are used in construction, and we see this all the time with builders that publish the photos on Instagram, like, oh, this is my metal seal pan under my window, like, you are shooting yourself in the foot. They don't actually know what they're doing. So main difference here is that you may see the little arrows here. The little arrows describe the heat path, the path for the heat to escape from the inside to the outside. And in the case of the metal, you see it causes, it causes a much lower temperature. So you may think the window is leaking, but it's actually condensation that is caused by the metal seal pan. And that is looking at the intensity on the right-hand side, the intensity of the heat flow. The metal flashing is so thin you can barely see it in this image, but you see the purple areas where the heat is escaping. And so you see it's much denser heat escape route for the metal flashing. So this is something that is very impactful in terms of causing mold and condensation. And this is where, with the buildings becoming more tight, we keep more moisture in, and we need to build our buildings better. And these kind of details are crucial in preventing mold and condensation. So if you think about buildings providing shelter for people, we don't want those shelters to be moldy. This is how we get there. And passive house, this is one of the hard requirements for certification. You do not need to certify, but you want to use this science to prevent mold and condensation. And building code is decades away from adopting this. So you can definitely have a building that is moldy and does comply with the most recent energy code. Then the second line item, before we get to energy efficiency, the first one was condensation. The second one is discomfort. And at face value, they both pick triple pane. So this is one of the things that throws most of first-time builders off. Like, you are getting a triple pane window, you may get a good one, and you may get a pretty poor one, and you're still paying the premium for the poor one. So this is why it's very important to look at this. To deliver a higher product, you need to have a much smarter, a more intelligent approach to it. Higher quality products don't happen just randomly. You just have to have a much more thorough approach to get there. Now, Enrico, on the left, has a beefy triple pane, it's filled with argon, has low E coating, and has an in install, meaning that the window is in line with the middle of the insulation. Enrique, on the right hand side, also has triple pane, but it's a skinny triple pane. It's filled with air, has low E coating, and has an Audi install, meaning the window installed all the way to the outside. And the U factor is basically the amount of heat losses that we have to that window. So if you see a U factor, think about losses, and the higher the heat losses is bad, and the lower heat losses is good. So nominally, both windows are triple pane, yay! But if you look at the actual losses, the one on the left that Enrico picks is a 0.13 heat losses, BTU per square foot per degree Fahrenheit per hour. So 0.13 as opposed to 0.26 of the other triple pane. So the triple pane that Enrico picked, probably because it was cheaper, but not necessarily. Some skinny and bad triple pane are actually more expensive than the good ones. Actually has twice as much the heat losses compared to the losses that Enrico's Windows has. And if you think about the infrared view, these two isotherm views, the rainbows here, show the black lines. The black lines are called isotherms. Those are lines with the same temperature. And isotherms are like lazy. They want to go slow and straight. They don't like to make curves. If the isotherms make curves in your model, it means that something is not going well, and that causes condensation or higher heat losses. So on the left-hand side, Enrico's has chosen to install the window in the middle of the wall insulation thickness so that the isotherms are actually going to go straight. So if you look at the isotherms at the bottom left, they're pretty straight in the middle of the wall, and straight up, if you draw a vertical line over the building section, that is where the glass is, so the isotherms kind of go straight, and they're happy if they go straight. Now, Enrique, on the right-hand side, has an Audi window installed. And if you look at Enrique's isotherm view, if you look at the black line in the rainbow picture here on the right-hand side, you see that at the bottom, the isotherms are in the wall. They are nice and straight and go up. And all of a sudden, they have to turn left to get into the frame and then up along the wall, along the glass, and then back out to the right, up to the wall. Isotherms don't like to do that. And if they do that, then it means that there's a lot of heat losses associated with those changes in direction. And that this is something tangible. The better window with the better glass, with the better installed details, in the Chattanooga, Tennessee climate, with 30 degrees outside and 0.13, 0.14 nominal versus installed U factor, that is something that leads to having an average temperature on the inside of the window of 65.8 degrees. This is science. This is not a plaque. This is not certification. This is actual building science. Based on the climate and based on the window installed U factor, you can actually calculate and quantify the level of comfort. And this is something that clients do care about. They will spend more money to get the better window. And Enrique, on the other side, has the skinny glass, has the Audi window installed, so he loses more than 5 degrees. His surface temperature is 60.6 degrees. So this is something that is noticeably colder, and sitting next to Enrique's window, you would feel the temperature difference. You feel it because our knowledge of thermal comfort tells us that if the temperature delta between the room average and the cold surface is greater than 7.6 degrees, then our body can tell the difference and we feel uncomfortable. So assuming a room temperature of 70 degrees minus 7.6 equals 62.4 degrees. So Enrique has discomfort because his temperature is actually lower, whereas Enrico has comfort. This is quantifying thermal comfort. This is the level of passive house building science that you can use in any project. You can use this to show your client why to get a better product to be more comfortable. And this is something that is very valuable for clients. So now we are switching to we looked at condensation, we looked at discomfort, now we're looking at the extra energy consumption. This is the graph showing the underperformance of Enrique's project. And this is the breakdown for heating and cooling, so we can have a better understanding of what's going on. And let's go through the different steps that we went through earlier. Starting from the walls, nominally both walls are R30. Enrico has cellulose plus 2 inches of polyiso, and Enrique has the same cellulose and basically 2 inches of polyiso installed on the inside of the zip R. But the zip R sheeting is a sheeting, so it gets a lot more nails, about 4 or 5 times more metal fasteners than the same amount of insulation, which is 2 inches of polyiso, that Enrico has. And that amount of extra nails does impact the performance of that R value, which leads to just those nails cause the building to consume about 4% more for heating. Think about all that metal. There's tiny little heat losses are shown here in the 3D model of the zip wall, and those heat losses cause the building to need more heating. Then for the roof, Enrico has the dense packed fiberglass, Enrique has the closed cell spray foam, and in a lab, closed cell spray foam performs at 7 R per inch. But in the field, it's actually closer to 3.5 or 3.6. In fact, in Europe, you see the source here is a German standard. In Europe, spray foam is rated at 3.5 R per inch. So this is something that significantly impacts Enrique's building, causing about 9% more heating and about 4% more cooling needed compared to the expectation. So this is just spray foam that is so difficult to do correctly in the field because of temperature and moisture that it's very easy for spray foam to underperform, and this is the impact that it has on the performance of the building. Then when we were looking at condensation, we looked at the metal sill pan under the windows, which has a dramatic impact on condensation, whereas in terms of the whole building heating and cooling demand, that little strip of metal under each window causes about 3% more heating. So this is just adds another drop to the bucket. Then the install position all the way to the outside for Enrique and in the middle of the wall for Enrico. This is the isotherms we looked at earlier. And this offset from the plane of the optimal informals that Enrico chooses causes a significant increase in heating, about 11% more need for heating for Enrique, just because he chose to install the windows all the way to the outside. Then for the glass selection, this is something that is actually interesting and has to do with how windows are rated. So at the top left and the bottom left, you see what I mean by beefy or skinny. We're looking at the overall thickness of the glass unit. So exterior pane, the 2 pockets, and the 3 panes. And for beefy, I mean 1.8 inch, almost 2 inches, whereas skinny is just 1 inch. And the reason this is important is most mainstream American window manufacturers have their frames developed to fit a double pane, because that is what code still requires in any climate zone in the country. There is no code requirement for triple pane glass anywhere. And because of that, all the big production window manufacturers have their frames set. They can allow an overall thickness of about 3/4 inch or 1 inch, which is typically optimized for double pane. Now, it is too expensive for them to change their frames to fit a triple pane. And so what they do is they just put an extra sheet of pane in between the two and call it a triple pane, but the triple pane remains skinny, and so it's not really gaining in performance. Or it's a triple pane, but it is not really increasing performance. Think about this. What is the best R value? If you have one panel of insulation 1 inch thick, or 2 panels of the same insulation 1/2 inch each. It's bullshit. It's the same performance. But they sell you a triple pane, so you pay the premium for the triple pane. The other side of this is that, because of this, the R value that you get from the glass for the beefy one is about an R10 for the glass, and this is including the argon, which we're going to see later about the losses in the argon fill and the durability of this R10 performance, as opposed to an R5 for the skinny triple. So they're both triple pane, so if you don't look closely, they're the same because it's triple pane, but one has double the R value as the other. Interestingly, in the US, the windows are rated at 0 degree temperature outside, And that condition almost never happens. And so in this graph here in green, it shows the exterior temperature of a typical year in Chattanooga, Tennessee. And the yellow horizontal line at the bottom shows the rating conditions for the NFRC, National Fenestration Rating Councils, that rates windows and doors in the US. And the one in orange, higher, is the European conditions for the European window and door rating. And if you can see, for Chattanooga and most places in the country, the European rating conditions are actually more relevant than the NFRC ones. So this is something that is impacting how products are developed in the US and how American products tend to underperform in the field because of this condition. Now, this difference between beefy and skinny glass leads to Enrique's window underperforming, and so overall, this underperformance caused Enrique's building to need 16% more heating. Then we talked about the solar heat gain coefficient, that is basically a filter or low E coating that you apply on the inside of the glass. And the two pictures on the left-hand side for the windows show at the top in yellow where the low E coatings are for Enrico's windows. At the bottom in red dashed are the coating for Enrique's. Now, that is where the low E coating are on the inside of the glass, because the coating itself is something that soft coating is just basically a powder that you can barely see that is spread over the glass, but if you pass a finger on it, you would wipe it off. So what these coatings do, they do reduce heat losses, but also they tune up or down how much energy we allow in from the outside, from the sun. So for Enrico, that was supported by an energy model, he picked medium solar gains, and so the coating that he picked allows about 37% of the energy from the sun into the building. Whereas Enrique, that was concerned about overheating, picked low gains glass, which only allow about 25% of energy coming in. And in Chattanooga is combination 4, so it's kind of in between, but it's still more heating dominated. Choosing low gains glass instead of medium causes the building to have about 19% more heating and 10% less cooling, because it blocks off more sun in the summertime, but it blocks the sun out in the wintertime. So the sum of the two is you still have more energy consumed because you have not optimized the coating on the glass. And without the support of an energy model, there's no way for you to determine this. This is project specific, this is climate specific. And if you are not making this decision on the type of coating based on an energy model, you're just guessing. And you can swing the performance of the building up and down just very randomly. Now, we talked about heat recovery ventilation for the fresh air ventilation system, and Enrique went for the ductless because he didn't want to deal with all the ducts for the ERV system. And these Lunos units are rated at 89% heat recovery. Unfortunately, that rating is based on a very inaccurate standard. This German standard DIN 308 is very inaccurate. The reason I say that is if your ventilation system has very efficient fans, then they move around the air without really causing much heat. An inefficient fan inefficient means it requires a lot of energy to do the job of moving air. And if it is inefficient, it means that it heats up a lot in moving around the same amount of energy. It means that a lot of energy gets wasted in form of heat. And so the standard here, DIN 308, does not account for this. And if your fan is inefficient, it means that it overheats while pushing air around, and that overheat may be read by the standard, DIN 308, as, oh, my ERV or HRV is actually recovering a lot more heat, whereas it isn't. So it is a very poorly set standard. And Lunos, unfortunately, only has rating, this very promising rating of 89% heat recovery, only with the DIN 308. Now, independent research shows that the actual heat recovery is much lower. It's not 89%. It's actually more in the realm of 68%. So that is, you have a significant performance gap in just selecting these units. So for the building, for Enrique's building, this leads to needing about 8% more heating and 2% more cooling. So looking at all these individual little drops in the bucket, this is now broken down, and we know what happened. And all of this is the underperformance that we encountered. And so compared to the promise that we had, we under-delivered because the building is actually needing 2/3 more energy. That is, a big fail for a high-performance building. Now, let's see how things age over time, and how does this higher performance stand the challenge of time. So we talked about an average family staying in the house for about 13 years before they move out again. And so what is the change in performance that we can expect from day 1 to year 13, once supposedly that family is going to move out again? So Enrico got argon-filled glass, and Enrique heard that the gas goes away after just a couple of years, so why bother? And so Enrique chose to have air-filled glass units. So at day 1, Enrico's glass has heat losses of 0.095 BTU per hour per square foot per degree Fahrenheit, because at day 1 the glass is 90% full of argon and 10% full of air, whereas Enrique's are 100% full of air, meaning that the losses are 0.213 BTU per hour per square foot per degree Fahrenheit. Now, 13 years after, you can typically expect 1% of gas loss per year from argon-filled or gas-filled glass units. A glass unit, if there's a major loss of the seal, that is where the moisture gets into the glass unit, and that is where the glass unit fogs up and you can no longer see outside. That is the main reason of failure for glass units, and that is not what we're talking about here. If everything works out properly, and most of windows do, then you can expect statistically 1% of gas loss per year. This is data that is supported by research both in Europe and in the US. So over 13 years, your gas would go down from 90% to 77%. Very important to also know that there is no such a thing as 100% argon fill. That is a lie. Do not believe numbers or do not believe manufacturers that claim that their glass units are 100% filled with argon. That is a lie, period. There is no technology today that allows to deliver that. So 90% argon fill is what we can expect at day 1. Now, 13 years after, with the glass units losing 1% of gas a year, it will go down from 90 to 77%. And the same glass unit with the same low E coating and 7% gas fill, the heat losses go up about 11% from 0.095 to 0.106, which compared to the losses of the air-filled glass unit, that is about 0.213, is still half the heat losses. So the older, less argon-filled glass unit is still outperforming the air-filled glass unit. So for Enrico, in this case, Enrique has no loss because he started off with just air to begin with. Enrico lost argon along the way, down from 90% to 77%, and this causes a little bit of extra heating. I did not write the percentages here, but it does cause some extra performance loss for Enrico. Now for the underslab, Enrico chose EPS and Enrique chose XPS. And XPS is nominally more performing than EPS because XPS has an expanding agent that insulates more than air, whereas EPS is just filled with air. So day one, XPS has R5 per inch, but after 10 or 15 years, that R5 drops down to about an R4. So this is, Enrique's underslab insulation is losing its expanding agent, so it's losing performance over time, and this causes some extra heat losses, which increase the need for heating in the summertime, and in Chattanooga, they reduce the need for cooling in the summertime. Then the air barrier, Enrico on the left had the poly membrane at the floor under the slab, had the tape sheeting at the walls, and a smart vapor retarder at the ceiling. That is the air barrier that Enrico has. And the air barrier is not what we see highlighted in orange here. What is highlighted in orange here is just the overall shape of the building envelope. This is not the air barrier. On the right-hand side, on the other hand, Enrique had the same poly at the slab, but used the drywall at the wall and the ceiling for the air barrier instead. Now, data shows that, I can actually be enlarged here. Data shows that for drywall, over 10 or 12 years, you can expect about 0.2, 0.19 increase in ACH because the drywall is not as durable. Whereas for smart vapor retarders and membranes, you can expect an increase in ACH 50 of 0.05, which goes back to what I started with at the beginning of this presentation. We are lucky that we EMU work with builders that really want to push the limit and do the best. And so in our niche, 0.6 is the bare maximum, but buildings hitting 0.3 or 0.4 is normal. So from a 0.4, if you go up 0.2, you almost double or you increase your air leakage by 50%, 40% by a lot, something that becomes noticeable. So that's why drywall is not a suitable air barrier for passive house. That's why because it's not durable enough. Whereas on the left-hand side, the other graph here shows a comparison with code minimum compliance. Code minimum compliance has a maximum allowed air leakage of 3 ACH50. So going from day one, 3 ACH50, you use your drywall and it starts cracking. You go from 3 to 3.2 is not a huge increase, it's like about 6%. But if you're really going for passive house or higher performance, then that is not, the drywall is not durable enough as an air barrier to guarantee the quality over time. This is the changes that this change impacts in terms of energy. So back to the year 13 expectation, we see a little bit of increase, like 2% for Enrico because of the loss in the gas argon as well as the increase in air leakage, minimal increase in air leakage. Whereas for Enrique on the right-hand side, after 13 years, the energy consumption for heating and cooling is now 3/4 higher than the initial one. So really much missing the mark on delivering the promised energy efficiency. So this was a story to explain what passive house can do for any project in improving the living conditions in terms of avoiding mold and condensation, delivering comfort and durability. So the closer we get to zero energy consumption in buildings, the more every single little detail matters. Think about the what we saw for the zip sheeting and all the little nails that you would not even consider in a regular project. If you're getting close to zero energy consumption, every single detail like that does matter. And keep in mind that we're not saying not to use zip RL. It's more like you need to be aware of that, because that you need to account for that extra consumption if you really want to deliver that super high efficiency to your clients. And whatever the project goals, the performance-based approach allows the team to make informed decisions at any stage of the project. It's really the handrail of building science that guides the project through different stages. And lastly, there are ways to deliver thermal comfort and prevent mold and condensation by design that code is not adopting. Code is decades away from delivering the quality, and Passive House delivers that today. So you can incorporate those methods to improve the quality of your product, whether or not you want to certify the building. So this concludes the presentation. Thank you for your time.